this lesson we're going to look at types of reactions. Specifically, our main focus is looking at acids and metals, acids and bases, acids and carbonates, respiration and corrosion. So let's jump into it with our first one, acids and bases. As we saw previously, acids and bases neutralize each other, but more importantly, as a chemical reaction, they form two key products. They always form water and they always form a salt. And specifically the type of salt can sort of be determined from the equation. So if we know that water is produced and we know what we started with, it's really just a process of elimination of figuring out what's left. So if we consider this first example, we've got nitric acid plus potassium oxide. So HNO3 is nitric acid. Ignore the two, remember that's just balancing. And K2O is potassium oxide. And this actually links back to what we talked about earlier in terms of ions. Because if we look at potassium and oxygen, we look at what kind of ion they would form, we will see that we need two potassiums in order to neutralize the charge of one oxygen. So we would know that K2O is the chemical equation for potassium oxide. That forms potassium nitrate and water. If we didn't even know that, if we didn't know it formed potassium nitrate, we always know it produces water. We can just look at what have we got left. Well, we haven't used a potassium, so we've got that. We haven't used a nitrogen. And the oxygen part's a little bit trickier. We nearly always have oxygen in these salts, so we can throw one in. But then from there we might go, all right, well, what's a Kn sort of thing? We're going to have a potassium nitrate. But you're not expected to actually be able to know or generate what that salt is. Just know that it produces a salt and water. Another example, sulfuric acid plus sodium hydroxide. So hydroxide tells us it's a base, sulfuric acid is an acid. So we've got our equation, forms sodium sulfate, which is a salt, and water again. So the key part here is that acids and bases form salt and water. Bit of a fun fact for you. The acid of a bee sting is actually what you feel. So bee stings, that sting that they give, some other animals or insects are the same. They actually have quite an acidic sting, but you can actually put bicarbonate soda on it, and bicarb soda actually neutralizes the sting that the bee or other wasps can actually produce. So you can use this concept of something like bicarb, vinegar. We've even heard of, I'm sure you've heard of things like peeing on yourself if you get stung by jellyfish. These actually are the same sort of concept, but often the problem with these is that they don't normally work. The reason they don't work is because the stinger is injecting into your skin, whereas for putting bicarb soda on yourself, you're just pouring on the surface, so it's not getting into the wound where it's actually burning. For something like a jellyfish, it's a little bit different because it's actually affecting the surface, so you can actually neutralize that. Let's look at acids and metals. So an acid plus a metal gives you a salt plus hydrogen. So H2 is hydrogen gas. So remember, so far we've said acid and base, salt and water, acid and metal, salt and hydrogen. So it's producing hydrogen gas. To look at an example, if we had hydrochloric acid and we add it to magnesium, so we're basically just putting metals in acids. We get magnesium chloride, which is a salt, and we get hydrogen gas. And I'll actually show you an example of a reaction in a minute that does this, and we'll do this in class. I'll show you how we can actually produce hydrogen from this. So acid, metal, salt, and hydrogen. So let's consider hydrochloric acid plus zinc. It gives you zinc chloride plus hydrogen gas. So you may have heard of the Hindenburg. It's the blimp. It's the photo that you can see here. So the Hindenburg disaster was because the Hindenburg originally, one of the earliest blimps, was filled with hydrogen. It was a readily available substance. It's lighter than air, so they thought, perfect, let's fill it up. Didn't really think about the safety risks of it, or at least didn't think it was significant enough. However, when it was moored to the station here, it generated a static charge and basically created like an arc of electricity across the gap, which ignited the hydrogen, and the thing blew up. But what we can use this for is we can use the similar sort of reaction that we see here to make an explosive balloon. So this is something that I'll show you in class when we do our experiments, that if you get hydrochloric acid and you add zinc to it, and a good source of zinc that's readily available is aluminium foil, contains some zinc. it produces the zinc chloride, so you'll see sort of this like solution in the bottom, but more importantly, it produces hydrogen gas. And you can actually get enough to fill up a balloon, and then I'll recreate the effect of the Hindenburg by igniting that balloon. You'll see just how volatile, just how explosive that hydrogen actually is. So just have a quick look at this equation. This was acid metal producing salt and hydrogen. Is it balanced? Hopefully you can say no. And if you were to balance it, what would you do? If we wanted to balance this equation, all we got to do is put a little 2 on the front, and we are done. So before we talk about acids and carbonates, let's talk about what a carbonate is. A carbonate is a compound that contains carbon. That seems pretty obvious, but specifically it contains 1 carbon and 3 oxygen. So it actually looks like this picture up here. You've got a carbon in the middle surrounded by 3 oxygen. 2 of them have these little single bonds, so we just call these single bonds. It's kind of how they're connected. And 1 of them has a double bond, and that's kind of important. The equation for a carbonate is CO3. So anytime you see like sodium carbonate, it's going to be NaCO3. Calcium carbonate is MgCO3. Magnesium carbonate is, oh, they've got these the wrong way around. That's not calcium, that's magnesium. Calcium's up here, CaCO3. Magnesium is MgCO3. What about this one? What would this be? CuCO3. It's copper. So we've got copper carbonate. So these are our carbonates. Anything with a CO3 is a carbonate, and conversely, if you know it's a carbonate, you know it's a CO3. So a really common example of a carbonate is calcium carbonate. This is actually a dietary supplement that they use when we don't get enough calcium. You often hear calcium is really important for bones. It's also important for muscles, nervous systems, and things like that. So they actually add it into products. You can also use it to relieve heartburn, indigestion, upset stomachs. So let's look at the reaction. Acids with carbonates form a salt plus water plus CO2. So it's almost the same as acid-base. We've got the salt and water, but we're adding CO2, carbon dioxide. So it produces bubbles. It's going to bubble away and produce a gas. But that gas is not hydrogen, it's CO2. So we can look at some examples. Calcium carbonate plus hydrochloric acid gives you calcium chloride plus carbon dioxide plus water. So we can use this process. If we've got a word equation, we can again identify what the salt is. We always know we've got carbon dioxide and water. So if we started with sodium carbonate and sulfuric acid, we're going to have the sodium, the metal, and then the salt part is going to be added. So we always keep the metal. So you see calcium, calcium chloride, sodium, sodium sulfate, copper, copper. So keep the metal, and then the sulfuric part just becomes sulfate. The hydrochloric becomes chloride. The nitric becomes nitrate. So we're seeing that pattern of what's being produced in our salts. The next example we look at is respiration. So breathing is actually a form of chemical reaction. It occurs in the cells of all living things, and we've seen this in our earlier topic when we looked at cellular respiration. But the simple sense is it's glucose, we add oxygen, and that produces carbon dioxide and water. The other thing it does produce is energy, because that's the whole point. We respirate to produce energy. However, energy is not a chemical that we're going to look at in this context, so we don't include it in the worded equation. And we'd write it as this. So glucose is C6H12O6, oxygen is O2, carbon dioxide we know is CO2, and water is H2O. And then we just need to go along and balance, and that's where the sixes have come from, just to balance out all the equations. So the process is always figure out the reactants and products, write the equations, then go back and balance by adding those prefixes, not the prefixes, the coefficients, to then balance everything out. So this is what I was talking about. We produce carbon dioxide, water, and energy, which we refer to as ATP, adenosine triphosphate. So that's a thing that the body or the cell uses as its energy source from respiration. The next one we're looking at is corrosion. So this is when we take a metal, we add oxygen to it. Remember, oxygen is O2. and it produces a metal oxide. Last topic, we talked about a really common example that we see on the land. That's iron oxide. So we start with iron, we expose it to oxygen, it chemically reacts and it produces iron oxide. So that's a version or a form of a corrosion reaction. So these corrosion reactions are what we typically know as rust. But if you want to be fancy, it's not rust, it's corrosion. It's a chemical reaction. There are ways you can stop it. You can inhibit rust through certain materials. Often what we do is we plate the metal. So we cover the metal in something that doesn't react. So a certain metal, things like chrome, we chrome plate things. The reason we do that is because chrome doesn't react with the oxygen. We need a very specific metal that will react to produce that metal oxide. So from here, have a go at the practice questions, and we'll continue next lesson.
Bye, have a beautiful time.